Oh, hello back. We're in chapter 4 now. If you remember the last time in chapter 3, we were talking about some inverses. Well, we're going to take this one step further and talk about inverse functions in depth. And why are we doing that? That's because we're going to talk about exponential and logarithmic functions in this chapter. And exponential and logarithmic functions are inverse functions. In fact, if you get half of it right, you're about 3/4 of the way there, really. So let's see how this goes. All right, you always want to start out with definitions. And sure enough, we have a definition of a function. So if we take a look at this capital F here, there we go. Take a look at the capital F, and we've got a function, and this particular function is defined using ordered pairs. Well, that's one way to define a function. And to get a one-to-one function, check and see whether reversing the coordinates will give you another function. So check out F, reverse the coordinates, and there's a new function, G. Well, not quite new, but it is a function, notice. All the x coordinates are the same, so we're going to have a function. Those are both functions, so that means that since we create an inverse and it's still a function, we've got a one-to-one function as well, and that is great. Now, what about this? The inverse of f, that's g. We just created it. For this function to have an inverse that's also a function, it means it's one-to-one. Every x value becomes y value, every y value becomes an x value. We just reverse the coordinates. Here's another way of looking at it. We're looking for one-to-one functions because they're going to be very special because they have inverse functions. This one is not one-to-one because even though it's a function, because every x value in the domain here is paired with exactly one in the range, the y values. However, when we reverse it, notice 7 is paired with a 2 and, let's say 3. I just went the wrong way. And it's also paired with a 2. That makes it not a function. And since it's not a function, then as a pair, we don't have one-to-one functions. Here's an example that is one-to-one. If we look at the x values over here, each one goes to a unique y value, and each y value goes to a unique x value. So this function is one-to-one. Now another way of determining this is if for every x values that are different, we always get y values that are different, then we've got a one-to-one function. Now keep that in mind. You might want to write a small note to yourself. A is not equal to B, those are x's, mean that f of A is not f of B. You got that? We're going to come back to that. This is another way of saying the same thing. Now, what am I talking about? I'm talking about a logical contrapositive. For every statement, you actually have 4 different statements that can be developed from that. The original statement, or just the statement itself. Next, you have the converse, and you have the inverse statement, that is, and you also have the contrapositive. Now, how do we get a contrapositive from some original statement? Let's sneak back here and take a look. This says that A not equal to B implies f of A is not equal to f of B. Let's go back. So I'm going to write this over here. A is not B implies that f of A is not the same as f of B. Now what's the contrapositive? The contrapositive is developed from this statement. And to do that, you reverse a lot of things. First of all, you bring the f of A and f of B first. F of A and f of B. But notice this statement here says they're not equal. Well, in the contrapositive, we say the opposite. We still have an implication, but in the opposite direction. And this A not equal B becomes A equals B. That's the contrapositive. The implication is reversed, and each of the statements is not only reversed in order, but it's reversed in its statement true false value as well. So for every two y values, if they're the same, that means they must have come from the same x values. That means you got a one-to-one function. Let's see if this function is one-to-one. Well, remember, what we want to do is prove that f of A equals f of B mandates that A and B have to have been the same. So how do we do that? We take this function, that's the one we're checking to see whether it's one-to-one or not. So first of all, what's f of A? F of A is -4. You put an A where the x is. There's your f of A. Now I'm going to sneak this backwards for a good reason. How about f of B? Because we need that as well. What's f of B? We put the B where the x is. We'll have -4 times B instead of the x plus 12. Now the reason I put these together is that let's see if these two are equal. Because if they're equal, we'll have a one-to-one function. So on the left, we've got -4a plus 12 equals -4b plus 12. And what does that say? Well, subtract the 12 from both sides. You have -4a equals -4b. Divide both sides by -4, and sure enough, A equals B. That means it's one-to-one, because we took this statement and proved that we are guaranteed the original x values, A and B, are the same. Just quickly here, I'm going to clear that slide so you can actually see this repeat as the slides do it. There we go. We've got rid of the x, or excuse me, we've got rid of the marks, and make sure I can still mark. So start with f of A equals f of B. We've got two y values that are the same. Can we prove that A and B are the same? There we go. F of A on the left, f of B on the right. If those are the same, subtract the 12 and divide by -4. Sure enough, it's one-to-one. Next, how about this? Well, again, we'll start with f of A equals f of B. We're assuming two y values are the same. So f of A means the square root of 25 minus A squared equals the square root of 25 minus B squared. So let's let the sides do the work here. We're going to choose f of a, f of b. They're different. And this is the other way of describing it. If we start out with a, not b, then that means their function values are not the same either. So this is the other way of doing it. This is the original statement, and the one we just finished is using the contrapositive. Either way will prove that a function is one-to-one. So there we put 3 in on f of 3, and we're going to put -3 in for f of -3. Notice we get a 4 in both of them. But because a and b were different, we were supposed to get different function values. So it's not one-to-one. Let's take another look at it. We look at this several different ways, so that you have different ways of determining whether a function is one-to-one or not. Well, if we've got the graph of it, lots of times we don't, but if we do happen to have that, we can use the horizontal line test. Well, maybe we should take a quick visit back to vertical line tests. Vertical line tests prove that you've got a function. If you have vertical lines and none of them cross the function at more than one place at one time, then you've got a function. Now we've got the horizontal line test. If it passes the vertical line test, and this blue curve does, you can't make a vertical line that crosses that blue curve more than one place at a time. So it's a function. Horizontal line test says if you can do it with horizontal lines, it's not only a function, but a one-to-one function. So if you start with any kind of function at all, and you want to know whether it's a one-to-one function, use the horizontal line test. And that'll do it if you've got a graph. So it's one-to-one if every horizontal line intersects the graph at most once. So it might be 0, it might be far away from the graph, or it might cross it once. If it crosses twice or more, it's not a one-to-one function. Just a reminder about the vertical line test. Next, you can see we've got a semicircle in this one we were just talking about. This function is not one-to-one because this line tells us it crosses the function at 2 places using one horizontal line, so it's not one-to-one. How about this one? Well, there's some lines that don't cross it. We don't care about those. Down here, we don't care. There's actually one in here that crossed it once. How nice! However, this line here, as well as a lot of other ones, cross it more than one time with the same line. So this is not a one-to-one function. How about this one? This is a line. Remember, the blue ones are the original relations or functions, depending on the case. Vertical line test, it only crosses it once anytime you draw one. And the horizontal line test, no matter where you draw a horizontal line, it crosses at most once. So it's not only a function, but a one-to-one function as well. Another way of looking at it is, if you've got a function, and if it's increasing everywhere as you go left to right, for example, or it's decreasing everywhere as you go left to right, that also proves that it's one-to-one. So to summarize that, y values being the same means the x values must have been the same to begin with. That makes a one-to-one. If you can prove that with the actual definitions of the function, you've got it. If every y value corresponds to exactly one x value, it's one-to-one. Third, if you sketch the graph, use the horizontal line test. Does it pass that? If it passes the horizontal line test, you've got a one-to-one function. Or if you've got the graph and you see it increases from left to right or decreases all the time from left to right, it's one-to-one. A sketch is quite helpful there. How about these functions? Let's choose some number from the domain of f. So we're going to start with f, and we're going to put a 10 in there. What is f of 10? We'll put 10 where the x is. Here's the x value. We end up with an 85. Now what are we going to do with that? Remember, we're talking about inverse functions. So we're going to take that 85 that we just got from f, and we're going to take that value and we're going to put it in g and see what happens. So there's 85. It goes in where the x's are in function g. What do we end up with? Simplify, and we're back to 10. Imagine that. Well, that's what inverse functions do. You start with one number, take the first function, take the result, put it in the second function, and if you end up with the original number, like we did here, we went from, where's my, there. We go from 10 to 85 and back to 10 again. F took us to 85, and G took us from 85 back to 10. That's how an inverse function works. Not only that, but if you start with G, put a number in, any x you like. Say, let's pick a 7. If you put a 7 in for G, took the result, whatever it is, and took it over to F, put in that function, you'd end up with your original 7 again. That's the definition of an inverse function. And of course, inverse functions only happen when we have one-to-one functions. One-to-one and inverse go hand in hand. So this is how this works. This is function f. Into f, 85 goes to g. I think they have these backwards. Yeah, this, for sure. This should be f here, and this should be g. Someone made a mistake. It wasn't me. So let's try some other ones. We tried with a 10. 10 went to 85, and 85 went back to the 10. We're going to go the opposite direction. Take the g of 3, and get a 29. Take that 29 to the other function, come back, you got 3 again. Use a -5. Go to one function, take that result to the other function, and you get the same number back again. You could try with fractions, anything you like. If they're inverse functions, that means they're one-to-one functions. That's what we can do. They're inverse, they undo each other. So this is one way to look at it. 2 is taken to the g function. It gives us a result, and that result is given to the f function, and we end up with a 2 all over again. Or the other way. Take the 2, put it in f, take the result, put in the g function, and we're back to 2. It has to work both ways. One way is not good enough for one-to-one inverse functions. Another way of putting that is whether we have f of g of x or g of f of x. In both cases, you end up with the identity function, just x. You don't have to go through all those numbers. Just see whether both of those directions take you back to the original number, which we'll call x. This is one notation for it. This is another notation. Think of the g here as the inside function and f as the outside function, because x gets to g first, so because it's on the inside, the result goes to f, and we end up with the original number again we had at the beginning. And the same in the opposite direction. Let's not keep this going forever. So, one-to-one function, and g is the inverse of function if we can take it both ways, and we end up with the identity function. Every x in the domain of g becomes a result or something in the domain of f. Inverse function. F is one-to-one. The inverse function is essential. Let's take a look at a few. First of all, we've got function f, x cubed minus 1, and function g, the cube root of x plus 1. Well, take a look at the graph. Horizontal line test here. We can't draw a horizontal line that crosses twice no matter what we try. Up here, one time. Down here, one time. No matter how low we went, we'd only cross it once. At most once. Also, if we take a look, I'm going to erase that again. There we go. Erase that ink. Take another look at it. Another way we can tell whether it's that we've got one-to-one inverse functions is if you start at any point on the function. Let's start with this point right here and travel from left to right. Are the y values constantly increasing or constantly decreasing? In this case, they're constantly increasing, so we've got one-to-one inverse functions. Check it algebraically. Remember, g gets it first, so the x goes into the g function first, which gives us this. The f function cubes the result and subtracts 1. What do we get? Simplify this. There we go. We've got the identity function again. Is that good enough? No, not quite. It's promising, but we have to try it in the other direction. We have to try g of f of x and see if that gives us an x as well. So we'll try it the other way. Simplify, and there's our identity function. We've proved it both ways, so it's a one-to-one, an inverse function. Now, a special alert. The way we read functions are if we start with a function f and we find we do have an inverse, we call that f and put a -1 up here as a superscript. That means that this is derived from the f function, but it's the inverse. Be very careful that you don't think this is an exponent. It isn't. This is a case where that -1 is used two different ways in algebra. Don't get confused with that minus 1. We're talking about inverse functions. Here's a picture of how the inverse functions work. Remember, we start with the blue one, so we start with this x. F takes us to y value over here. Then we go with the inverse function, goes backwards, and we end up where we started. Inverse functions, 1 to 1. Here's an example that has ordered pairs, which makes it pretty simple. What's the inverse of this function if it's 1 to 1? First of all, is it 1 to 1? Unfortunately not, because if you look at these two, the 1 and the 2 are different, but the y values are not the same. So it's not 1 to 1 and does not have an inverse. We can reverse those coordinates all we want, but the reverse is not a function. The reverse relation is not a function. How about this one? Well, first of all, you can see that all the x values are different, so it's a function. Are all the y values different? Yes, that's a function as well. So we've got an inverse function, and we can write it like this. And we can write the order pairs. I'm not going to do it, I'll let you do it. Take each one of these order pairs, reverse them, and we'll have the inverse function. And there you go, the inverse function. Notice that if you look at the collection of x values here and the collection of x values here, the domain in one becomes the range of the other. We're reversing the x and y coordinates, so of course. Now here's a semi-example. We've got a function here. Notice that every year we've got a certain number of hurricanes. It's a function. And also notice that for this collection of years, if we take the number of hurricanes, we always get it paired with a unique year. So it's 1 to 1. And we can reverse those like this, and we've got the inverse function. It's an inverse of the original, and it's a 1 to 1. Now, how do we find that? If someone actually gives us one, I'm just going to make up one here on the fly. Suppose we had the function 3x minus 2. Can we actually find f inverse if it exists? Well, yes, we can do that. It takes 3 steps. It might take a little bit more work than it sounds like, but 3 steps. Swap the x's and the y's in the original function. Solve for y and replace the y with the inverse notation. Now, what does that mean practically? Well, let's take a look at this, for example. First of all, I'm going to move over here so that we can see what comes on the screen later. We have f of x equals 2x plus 5. First thing we do is we're going to write it using y instead of f of x. It just makes things a little bit easier. There's the same function. Now, next thing we do is we exchange the x's and the y's. So we get x equals 2y plus 5. And now solve for y. Well, we're going to subtract 5 from both sides. That'll give us 2y, I'm going to switch them here, equals x minus 5. And then divide by 2. And we've got y equals x minus 5 over 2, which if we choose, we could write as 1/2 x minus 5 halves. Last, we'll write it in inverse notation. F inverse of x equals 1/2 x minus 5 halves. There you go. And you can graph both. Both of them pass the horizontal line test. You can check that for yourself. Well, almost every line does anyway. Any non-horizontal line will pass the horizontal line test and be a one-to-one function. So you can take any linear function and create its inverse. So how about this one? Okay, swap them. Start solving for y, and we've got it, and then change the notation to inverse notation, and you found the inverse of the original function. It's just undoing things by swapping the x's and the y's. How about this one? This one is a little bit different. Notice we can't tell just by looking at it, maybe, that it's a one-to-one function and has an inverse. Notice that you've got y, that's good, but you have an x squared. That's not a linear function, so we're not quite sure. We have to actually check it out. It's a parabola. In other words, the graph looks something like this. And it's a function because every vertical line hits it once, but horizontal, there's one that crosses it more than once. It's not a one-to-one function, and therefore it does not have an inverse. If you work with the equation, you can end up with the same result. There's the original equation. Swap the x's and y's. Solve for y, and y equals, because you've got a square root, there are two answers, the positive and the negative. And since a y value has two possible x values, it's not a one-to-one function, and y equals x squared plus 2 does not have an inverse. There's the graph of it, and you can see that it's a function on this one, but notice that this one, it's different from the last one. Remember, this was the last one, x squared plus 2. This is x minus 2 cubed. Cubed is the key. You'll have inverses. You might want to remember this, but you might need to show it. You'll have inverses if this exponent is odd. If it's even, you will not, because you'll have square roots or fourth roots or sixth roots which have positive and negative x's. Also notice that as you go from left to right, this function keeps on increasing. Another reason why it's one-to-one, it has an inverse. What's the inverse? Okay, we'll switch to y instead of f of x. Swap the x's and y's. Put the function in. Now you've got the cube root of x equals y minus 2. One more step. And you've got y. And the last pseudo step is changed to the inverse notation. And you've got an inverse. And of course you've got one-to-one if it's an inverse. How about a rational function? These, remember, are a little bit trickier because you can tell right away that x could not equal to 4. But if you stay away from the 4, it's a one-to-one. Not only that, we can find the inverse. Switch the x's and the y's. Got that? Now multiply both sides by y minus 4, and that's legal because the y isn't ever going to be a 4, so that's a good fraction. Multiply both sides by the y minus 4. Here you go. Simplify or multiply that out or distribute, whatever suggestion you have for wording. Solve for y next. Bring the y's to one side. Factor out the y. That's an important but sometimes forgotten step. Then divide by the x minus 2 because you want y. And last, you put in the inverse notation and you are done. You've got the original function up here and its inverse down here. And remember too that we've got a restriction up here, x is not equal to 4, and down here x is not equal to 2 because of the denominator. And remember, each is an inverse of the other. It's not just f has an inverse of negative its inverse. The inverse has an inverse of the original. Does that make sense? All right, so if you're going to graph it, one way to graph it is find some ordered pairs, as many as you can, for f. And that should be pretty easy. Just put numbers in for x, find what the y values that go along with it. Get plenty, because if it's not a line, you're going to need 6, 7, 8 points before you get an idea of what it looks like and how to smooth in the curve. Once you've got those ordered pairs, a bunch of x, y pairs, then swap the x and the y. That will help you graph f inverse. Plot those points, sketch the graph, draw a curve or whatever it is through all of them. So here are points on, this is a point on a function. The function f takes a to b. In other words, f of a equals b is what this means. Now if you take this point that's on function a's graph, reverse the coordinates, and you've got a point that's on the inverse graph. So if you get a lot of these points, reverse the coordinates, graph them, then you can graph the inverse function. Notice also that this y equals x is the line about which you could sort of twirl the original function and end up with the inverse. So imagine just taking the whole coordinate plane and twisting it around that y equals x. This point will move over to here, and all the other points will move over to the inverse. And you can graph it. Remember, they're mirror images around y equals x. Now, the thing to remember most of these is that the original function is blue, the inverse is in red, so that you can compare them. And next slide we'll have an example of another one of those. And remember, this is the original function, and if you take y equals x, sort of twirl around with your fingers, this blue line becomes the red line over there. Notice this point moves over there, this point, this point moves over there, and the same distance, by the way, too. Going from blue straight to the y equals x, and on the other side, the same distance would be on the inverse. A better example over here, we're starting with this one. Each of these points, if you take a perpendicular to that y equals x, go the same distance on the other side, get the corresponding point on the other side, which is on the inverse function. So take those blue points, switch each one the x and the y values, and you get points on the inverse function. So these points get converted to these points. Okay, so let's take the inverse of a function with a restricted domain. Why is it restricted? Well, take a look at that x plus 5, where it is. It's inside the square root. If it's inside the square root, then this has to be, put it this way first. This x plus 5 has to be either greater than or equal to 0. And solving for x, that's the restriction. So notice the domain is starting at -5, going up to positive infinity in this case. Remember, you have to think about what numbers can be used inside the square root. Cube roots are okay. Fourth roots, square roots, no. Even roots, you've got a restriction. So we'll start with that function. Put the y in where the f of x is just to make it easier to work with. Swap the x and the y. It's messy if you don't do that, by the way. And solve for y. Square both sides. That looks a little bit better. And get y by itself. Last of all, put the inverse notation in. And there's your inverse function. Right there. With the restriction. Okay. Here's another picture similar to one we had before. Remember, the blue is the original function. If we twirl that one 180 degrees around y equals x, we end up with the red curve. Hope that picture that I drew didn't throw you off, but the original picture on the side is good. So some things to remember about inverses. If you've got a one-to-one function, there we go. If you've got a one-to-one function, you have an inverse. You might have to find it, but one exists. Second, the domain of f is the range of the inverse, and the range of f is the domain of the inverse. So the domain and range interchange with some restrictions occasionally. If AB is on the graph of the function, then BA will be on the inverse. To do it algebraically, you can also take the f inverse, replace f of x with y, interchange the x and the y, solve for y, put in the inverse notation, and you've got the inverse function of that original function, f of x, also known as y. We can also use that. Now, we're going to use a simple example here because cryptography can be quite challenging. A one-to-one function allows you to do some cryptography. And what am I talking about? I'm talking about taking a message, making it so you can't tell what the message is, and then on the other side, putting that message back together. So this is you, and this is your friend, and your secret message you send across. Someone looking at it as it's going across can't tell what the message is, but your friend has a decoder, and they can figure out what the message is from what is going across, maybe wires, for example, or wirelessly. Now, this is what I'm talking about. So, first of all, each letter corresponds to some number. Let's do it really, really simple. A corresponds to 1, B to 2, all the way up to Z will represent by a 26. Now, here's a message. Be my Facebook friend. The first thing we do is take each of the letters, like the B. B will be represented by a 2 in your initial message. E is a 5, M is a 13, Y is a 25, and so on down the line. However, if you send that and someone intercepts it, it won't be too hard to back off of that and say, oh, number 2, I bet that's a B. 5, I bet that's an E. That's not good. If this is a secret message, you don't want someone to be able to do that. So, use this encoding. We're going to encode it. We're going to put it in code. So for each of these numbers that you got from the letters, put that number in for X, and you'll get what you're going to send to your friend. So for example, we start with a B and Be My Facebook Friend. First of all, that's the second letter of the alphabet, but we don't want anyone between us and our friend to know that. So we take F of 2, notice what the function is up here. For F of 2, we're going to take 3 times that 2, add 1, and that gives us a 7. Now, someone looking at the 7 in between you and your friend will look at that and say, 7? Hey, that's a G? I'm not sure what the dickens it is. But when your friend gets it, they take the 7, perform the inverse operation, or the decoder, and they can get that 2 back again. They recognize the 2 as a B. First letter of your message that you encoded and sent over to your friend. Continue doing that, and you can send a message. People in between won't know what it is, but your friend will say, oh yes, of course, I'll be your Facebook friend. So take each one of these, code them. There's 7 for the B, 16 is what the E becomes, 40 is what the M becomes, and so on through. When it gets to the other side, this is the B encoded, E encoded. On the other side, your friend gets this message, which doesn't make any sense by itself. They decode it using the inverse. Here's the inverse that your friend is going to use, and the decoding takes that 7 that you sent and puts it back to 2, which is a B. Take the 16, put in the decoder, it's a 5, and that 5 corresponds to E. Well, you've done some cryptography, friends. How about that? You want to be my Facebook friend? Fine. Send me a message, and I'll probably say yes. Okay. You take care. Get a few extra Facebook friends, maybe. And we'll see you next time, as long as you keep smiling. Bye-bye.